remind you that we're talking about a process here. And so we're going to use this process to figure it out. Now, I'm also going to remind you I gave you a more extensive version of this, right? You have it, you have access to it in your notes, so make sure you use it. Um, there's not really cutting corners here so much. Um, you're going to have to decide if this is a first law problem or a second law problem. What do you guys think? Why? Yeah, it says it. It says it very clearly that the object's going to accelerate. That makes it a second law problem. So that'll be my starting point. I have to draw a free body diagram to try and figure out what forces are acting on my object. So I'll reduce the box down to a dot. And we've done this one already. You have probably one similar in your notes, but I'd encourage you to try these on your own without having to look at your notes. Let's name some of the forces that are probably acting on our object. Can you name one? So the weight, I have to draw a single arrow straight down and label it weight. What's another force acting on my object? Normal force in contact with the plane. So I have to make that perpendicular to the surface. So as I go to draw it, be mindful that it has to be perpendicular to your surface. So there, perpendicular to my surface. I'll label that normal force. Anything else? Yeah, there's friction acting in the system. We're told there's friction. Now, friction has to be drawn in such a way that it opposes the direction of motion, and it has to be parallel to the surface, which makes it perpendicular to the normal force. These are all rules. No decision has to be made there. So you just need to know the rules. So I think that's about it. I can't think of any other forces that are acting in my system. So now I need to apply a coordinate system, something I can use to break my forces up into the x direction and the y direction. So when I choose my coordinate system, I told you guys that there are two priorities you should use in choosing your coordinate system. The first priority I said that you should use is make sure it's directed in the direction of the acceleration. And since this system is accelerating, you got to use that. So that doesn't give you many choices so much, but it gives you at least a starting place. I'm going to take my coordinate system and direct it that way. Remember, I get to choose what's positive and negative, so I'm going to choose to make the direction the system's accelerating the positive x direction. And I'm going to choose to make up the positive y direction. Now I have an off-axis force, and because I have an off-axis force, I'm going to have to break that force up into its components. So the weight is the off-axis force. This angle is 40 degrees. So I'm going to take the weight and break it up into a component that is downwards and a component that is down the ramp. Those are my two components. This is going to be weight cosine theta. This will be weight sine theta. Any question about those choices? Okay, if you didn't get this far, stop right here, write yourself some notes. What do you need to do different tomorrow? Okay? Because if you have no questions for me and you didn't make it this far, you need to write yourself some information. Am I good to go on? The last step is just to apply the rules. And we said it's a Newton's second law problem. So to apply the rule, I'm going to first say the net force in the x direction is the one that's accelerating. So I'll apply that rule to the x direction. We selected the x direction to be the direction of the acceleration. And then the net force in the y direction has to be 0 as a consequence of doing that. In the x direction, I only see two forces. I see the frictional force, which is going to be negative, and weight sine theta, which is going to be positive. So weight sine 40 degrees minus friction equals ma. Now in the y direction, I see two forces as well. I see the normal force upwards. I'll make that positive. and I see weight cosine theta downwards. I'll make that negative. Now that's the force concept model. That's what it gives us. It gives us relationships. Now, if those relationships can be used to solve our problem, great. If they can't, then we're going to need other information. I think that this is going to be enough information to solve our problem, though. Just looking at it, I'm going to replace weight with mg. I'm going to replace m with the mass of the box, which is 2. I'm going to replace a with the acceleration we were given. That was 3. Looks like I can figure out the friction from here. So let's do that first. So mg sine 40 minus friction equals ma. 2 times 10 sine 40 minus friction equals 2 times 3. I think that'll solve for friction. And you do so, you get 6.9 newtons. Now, next you're asked to get the ratio of the frictional force to the normal force. So that ratio is just friction divided by normal. I have friction, but to finish this off, I'm going to need the normal force. I think I have a method to get the normal force as well. The normal force is going to equal mg cosine 40. I believe that's 15 point something. I can't remember exactly what. 15.3. There you go. That gives you a ratio, 0.45. All right. I want to add to this today, but we okay with this so far? It's not terrible. We've got some terrible ones coming though. So let's try and get these down. Now will be something you should be attempting. This ratio is called the coefficient of friction. It tells you how much friction you get for your normal force and is a description of how rough the surface is. Surfaces that are rougher will have a higher coefficient of friction. Surfaces that are smoother will have a lower coefficient of friction. The coefficient is the ratio, and it tells you two things that you need to really understand. First, there is no friction without the normal force. The normal force is how hard the surfaces are pressing together. So the normal force creates friction. Now, how much friction you get for your normal force will depend on how rough the surface is. So rougher surfaces are generally going to have a higher coefficient of friction, while smoother surfaces will have a low coefficient of friction. In fact, those two words can be used on the exam to indicate whether a surface is friction-free or not. So if they say a rough surface, they are telling you the surface has friction. If they say a smooth surface, they're often telling you that the surface has no friction. So the words rough and smooth are actually vocabulary words when it comes to test questions. So again, smooth that generally refers to surfaces that have no friction or very low friction, and rough surfaces refer to surfaces that have a certain amount of friction that's detectable and is going to affect your problem. Now, friction, we know that there are two types. There's static and there's kinetic. The problem we just did was about kinetic friction. Kinetic friction is also called sliding friction. And it has to do between surfaces where one surface is moving with respect to the other. So this one, there has to be either a velocity that is constant or an acceleration. So there has to be one surface moving with respect to the other. In these circumstances, the kinetic friction will be equal to the coefficient of friction. That's a symbol, and I'm going to talk about the symbol in just a minute, times the normal force. Now, the moment I start putting symbols up here, people start getting a little weird. So I want to, we all heard that, right? Okay. It's just a symbol, it's a letter. But again, we use a symbol for this. We use the Greek letter mu. And because, again, that's a symbol, it tends to make people get a little weird. And it's also got a big name, coefficient of friction. It's just a percentage. The coefficient of friction generally is a number between 0 and 1. And it represents the percentage, how much friction you get for your normal force. But we use the Greek letter mu, which is like a U with a little flare. It's drawn kind of like that. At least when I draw it, that's what it looks like for me. But it should have a little tail that hangs below the line and have a U that's on the line. When it's typed, the flare part is usually straight like that, like you'd expect for like a P or something like that. But when it's drawn more cursive-like, it has a little more flare. In this case over here, we're going to put a little K next to it to indicate it's the coefficient of kinetic friction. Now, all surfaces will have both kinds of friction, both static friction and sliding friction. So kinetic friction is what happens if you get your object and get it sliding. But before that happens, when this object was at rest, and that's static friction, often called starting friction. In this case, all problems that involve a static frictional force are going to be Newton's first law problems because the surface is not sliding with respect to the other object or the other surface. So they're stuck together. This one's a little bit harder to understand because static friction is a responding force. This is the first time you've heard me say the word responding force. But normal force and static friction are both considered responding forces in that the forces respond to the situation at hand. The thing about static friction is that if you have a surface or you have an object that is experiencing static friction, the static frictional force will continue to increase until it reaches a maximum. I'm going to demonstrate real quick. Yeah, an inequality is that simple. So that's the frictional force has to be less than or equal to some maximum. And that maximum is going to be a different mu, the static frictional coefficient, times normal force. The thing about static friction or starting friction that you have to get into your head right away is that the starting frictional force can be any value between 0 and this maximum. This represents a maximum. So if your system is not moving and you have an idea that there's static friction, you don't necessarily know how much friction there will be because it can be any amount up to this maximum. So unless you know you're at the maximum, you have to work with an inequality. And my understanding from working with you guys is you're not always great about working with inequalities. So we're going to look at some situations today where you have to work with an inequality, okay? Now, if you are not great at working with inequalities, you're going to hear me use this phrase quite a bit, that you always substitute into the equation that has your inequality. So whenever you're going to use an inequality, you're going to have to substitute into that equation. And I'm going to show you how it's done, okay? This one I think will be a little more straightforward for you. Let's go back to the exact same problem we just looked at. That way it's fresh in your head. And we're going to kind of repeat it. Okay? So we have a static frictional force. We have a static coefficient of friction of 0.7. Okay? I'd like to find the maximum angle I can open up the book before the box will start to slide. Okay? Does everybody understand what the question says? Maybe if you're trying to keep notes, maybe write the question down. What is the maximum angle we can open up the book before the calculator will start to slide off the book? Now, is this clearly a first law problem? Yeah, we want the calculator to stay in place relative to the book. That makes it a first law problem. So we'll start by saying clearly, this is a first law problem. Now, you now know more things. So one of the things you have to start to add into this is that sometimes there are equations you're going to bring to the table that are in addition to what you're going to develop when you're using Newton's first law. The equation we're going to bring to the table is knowing that this is a static frictional force problem. So I'm very likely going to have to use this at some point. So these are two things now I can bring to this problem: Newton's first law and the definition of static friction. Now, I chose this as our starting point because we just did this question, so I don't think we have to spend a whole lot of time putting this problem together like we did a moment ago. Would you guys agree with that? Like, we know what this one's going to look like. We're going to have our three forces. And the difference is they're all balanced. So I think we can speed ahead a little bit and get to the point where we are breaking our forces up into their components. So I'm going to try and move to that point here. We don't know what theta is this time. We're trying to find it. But I'm still going to be doing the problem the same way I did it before. I'm going to take my off-axis force, and I'm going to break it up into components. I'm going to make this one sine and this one cosine. But here, net force in the x direction, I'm going to set that equal to 0. And net force in the y direction, I'm going to set that equal to 0. So this part of the problem still works out the same way. I'm still going to have W sine theta minus friction equals 0. And W cosine theta and normal force equals 0. And all of that's still the same. So I want to keep reminding you that this procedure of four things still works the same way every force problem. And in every circumstance, it's going to generate a couple of relationships that you may or may not be able to use to figure out your problem, but that's where you're going to start. Now, our job is to figure out what theta is. So I'm going to bring all the parts of our problem together. So we have these things. Now, whenever you're tasked with dealing with an inequality, I'm going to tell you the best way to deal with the inequality is to substitute into your inequality. You'll find that to be the best way to deal with the inequality. It lets you know what side is supposed to be less than or greater than something else. In this problem, we're trying to figure out what theta is. And I see a plan that involves substitution to maybe where I can get theta by itself. But to do so, I'm going to have to substitute between these three equations. So whenever you're faced with inequality, substitute into the inequality. So I'm going to substitute into the inequality here to replace the normal force with something else. And I'm going to substitute into the inequality here to replace the frictional force with something else. Because we have from here that the normal force equals mg cosine theta, and here the frictional force equals mg sine theta. And we know the mass of the box. We know g, so those seems like good things to do substitution with. So again, I'm going to substitute into the inequality, which is going to give me mg sine theta must be less than or equal to mu s times mg cosine theta. I just substituted into the inequality. This preserves the inequality, and it tells me where my thresholds are. Everybody see what I've done? Now I can cancel some stuff out. Apparently the mass of the calculator doesn't matter. So I can cancel that out. Actually, it looks like g doesn't matter either. I can cancel that out too. But that does leave me with sine theta on this side has to be less than or equal to mu s times cosine theta on this side. We're trying to solve for theta. Can you see a method to solve for theta here? What's the method? Go ahead. All right, so I'll divide both sides by cosine. That gets rid of it on this side, and sine over cosine is tangent. So I get tangent of theta has to be less than or equal to mu s. This is a threshold, right? It's telling me that my angle has to be less than or equal to this value. Now, to figure out the value, of course, you would then have to do your substitution and put your numbers in. So when I do this, 0.7 inverse tan, it tells me that if I don't want the book to slide, I have to keep my angle less than 35 degrees. And that's what it tells me. I think we should probably do another one. What do you think? A similar level of difficulty, okay? But a little bit different question. I want to challenge your algebra skills a little bit. Bless you. Actually, no. I know you guys don't know what this is. It's a sled. In other parts of the country, they have them. We don't see them very often. All right. So you got a 20 kilogram sled and a handle that makes an angle of 30 degrees. You're going to pull along the handle. I want to know, how hard do you have to pull to get the sled to start moving? There's a coefficient of static friction of 0.5 between the sled and the ground. So how much force would you have to apply to get the sled to start moving? This one's got some good chops to it. But the real part of this problem is you guys dealing with the forces in this problem. So I'm going to stop here for a minute. You guys follow our set of steps, generate a couple of relationships. Can't really do this problem until we do that part. So generate our two relationships. Okay, is this a first law problem or a second law problem? Still first, right? The sled's not going to move. We want to find out how much force to break friction, but we're still using the fact that it's not moving. So this is a first law problem. So free body diagram. Walked around, saw some struggles. So do you have a picture that looks like this? One of these, I assume? And maybe one of these, I assume? And maybe one of these, I assume? And maybe one of those? Is that what yours looks like? So if you're saying no, I don't think I've drawn these well to scale, to be honest, but that's how I see it. Start with the weight, and there's the force of you pulling on the wagon. It's in contact with the ground, so the normal force has to be perpendicular to the ground, and friction has to be parallel to the ground. So I think this is our arrangement. Now, I think I didn't draw it very well to scale, but oh well. Now I have to choose a coordinate system. The system's not accelerating, so I can choose any coordinate system I want. I'm thinking I'm going to choose a coordinate system that's lined up with the most number of forces possible, so I don't have to break many into their components. So that look like a good choice? I think so. That's a great choice. I don't have to use this one, but which one would you use then if you don't use this one? I'm going to make this the positive x direction and this the positive y direction. I am going to have to take my tension and break it up into components, right? Because that's the one that's off axis. So I'll have tension cosine 30 and tension sine 30. All right, that takes us all the way down to step 4, where I have to apply Newton's laws. I have 2 laws to apply here. Net force in the x direction, which equals 0, and net force in the y direction, which equals 0. In the x direction, I only see 2 forces, right? This one and this one. Now, did you guys see? So T cosine 30 minus friction equals 0. In the y direction, I see 3. I see this one, and this one. That all good for you guys? All right. So T sine 30 plus normal force minus weight equals 0. All right, that takes us to the end. That's generating relationships. We have 2 relationships we've generated. Now that I've done that, this is what we're going to work from. Now we're trying to figure out how big the tension force is. That's our goal. How hard do I have to pull on the handle? And I see the tension force in 2 places, and I don't think I can solve for it in either one, because I don't know how big the frictional force is, and I don't know how big the normal force is. I'm pretty sure I have the weight, because it's a 20 kilogram sled, so I have mg. I can get that. And I know the coefficient of friction's involved, so it probably makes sense that this is going to be involved. Again, you'll notice one of the things that's happening here, if you want something that helps your notes, friction bridges the x direction and the y direction together. It provides a way to set something in the x direction and something in the y direction together. It brings them together, right? Because it's got both friction and normal force in it. So it tends to bridge those 2. I've got an inequality though, so as you might have guessed, I'm probably going to use the inequality here, which means I'm going to substitute into this formula. So I'll solve one of these for friction and one of these for normal force. So when I solve for friction, I'll get friction equals T cosine 30, and normal force equals weight minus T sine 30. Now some of this makes sense, that the normal force is going to be less because I'm pulling up on the handle. So that's why the normal force isn't equal to the weight, because you're pulling a little bit upwards. Does that make sense? All right. I'm just going to substitute this in now. Now this part is going to scare some of you, but I don't care. Don't be scared. It's just stupid math. So T cosine 30, that's the friction, plugging in right here, less than or equal to mu s times weight minus T sine 30. Now you have to solve that for T. Now that part is just algebra. That's not my class. You're supposed to come in with that skill set. My experience is that you guys have a lot of difficulty doing this. It might be easier if you put all your numbers in if you want, but you should be working these out algebraically first. Because as anybody will tell you, your test is probably more likely to have something without numbers at all than is. I would encourage you to always work out the math first without any numbers and put your numbers in at the end. So that's what we're going to do here. So how do you guys feel? Do you feel like you can isolate T with your skill set? You should try. I will give you a hint. Distribute the coefficient, and then get anything that has a T on it on the same side of the equation. Start there. I'll give you a second. You should get ahead of me. Okay, I skipped ahead 2 steps. Do you guys see what I've done to get here? I distributed the mu first. That got rid of my parentheses. I added this term to both sides. That got the t's together. Now, again, I'm trying to solve for t, so I'm going to factor the t out. Now I just need to divide, right? Do you guys see that? So I'll divide both sides by all of this. Now, I know some of you are going to have trouble, but the algebra parts of this got to become good at. Yesterday I was grading somebody's retake and I saw this. I took a picture of it, sent it to all of my work friends, and says, yeah, we're going to do calculus, but we have to deal with this first. And some of you don't know why this is funny, and that scares me even more. But this is not equal to 3. This would be equal to 4.5. So let's get our algebra under control, okay?